Before there were oceans or mountains, the universe was filled with massive clouds of molecular gas. These structures stretched for light years across the dark vacuum. Eventually, gravity disrupts the silence. A distant explosion causes a pocket of gas to collapse. The cloud spins, heating up and compressing rapidly, until a blinding new star ignites at its very center. Not all of the material falls into the newborn star. About 1% of the dust and gas is left behind, flattened out by rotation into a massive, spinning halo known as a protoplanetary disk. Building a star is mostly a matter of gravity pulling immense amounts of hydrogen together. Constructing a solid planet from the scattered microscopic debris orbiting that star is significantly more difficult. In the early solar system, tiny dust grains must bump into each other and stick. As these small clumps grow to the size of pebbles, they begin moving faster.
When they collide at these higher velocities, they bounce off one another or shatter back into smaller fragments. Astronomers refer to this as the fragmentation barrier. The longer the material stays trapped at this microscopic size, the more vulnerable it is. The intense radiation from the young star pushes against the dust, threatening to evaporate its ice and blow it out into deep space. If the debris cannot bypass this bouncing phase, the entire disk will be swept clean. The star will burn alone, and no planets will form. The mechanism that allows solid matter to survive is a process called pebble accretion. This diagram illustrates a cross-section of the young system. The disk isn't empty, it's filled with thick gas orbiting the star. As centimeter-sized pebbles travel through this environment, they experience aerodynamical friction, a drag force from the gas that drains their forward momentum. Losing speed forces the pebbles to drift inward. As countless pebbles slow down and migrate, they bunch up, clustering into dense, swirling filaments of rock and ice. When the density of a filament reaches a critical mass, the entire swarm collapses under its own gravitational weight. Millions of pebbles are instantly crushed together into solid masses 100 kilometers wide. By forcing the material to collapse collectively, gravity bypasses the fragmentation barrier. These new rock bodies, called planetesimals, are too heavy to be blown away, securing the foundation for planetary growth. Further out in the disk, past a boundary known as the frost line, the temperature is cold enough for water, methane, and ammonia to remain frozen. Ice provides an abundance of sticky, raw building material. Here, planetesimals collide and merge rapidly, assembling into massive solid cores that can reach 10 times the mass of Earth. Once a core hits that size threshold, its gravity is strong enough to begin capturing hydrogen and helium directly from the disk. The growth rate accelerates as the young planet vacuums up the surrounding atmosphere. This image of Jupiter captures the result of that runaway accretion. Gas giants emerge from the dust in a fraction of cosmic time, sweeping up the bulk of their mass in as little as 10,000 years. Because these giants reach such immense proportions while the disk is still full of material, their gravity acts as an anchor, dictating the orbits and survival of every other forming world. In this orbital model, we see the grand tack hypothesis in action. Gravitational interactions with the gas cause Jupiter to migrate inward toward the Sun, acting like a destructive cosmic snowplow. As it pushes inward, Jupiter scatters asteroids and planetesimals out of its path, clearing out the building materials and limiting the matter left behind to form Mars. Closer to the Sun, the remaining heavy elements had formed dozens of rocky planetary embryos. This region was a violent construction site, with young worlds routinely pulling in smaller bodies and crashing into each other. About 4.5 billion years ago, one of those surviving embryos, roughly the size of Mars, collided directly with the young Earth. The impact vaporized vast amounts of rock, launching a ring of debris into orbit. This material cooled and clumped together, forming the Moon and leaving the lunar surface marked with the physical evidence of this impact history. This collision tilted Earth's axis to 23.5 degrees, creating our seasons. The newly formed Moon stabilized Earth's rotation and created the tides, turning a molten sphere into a world with predictable, stable cycles. Over the following millions of years, The sun's radiation stripped the remaining gas from the solar system. The smaller, unstable rocky worlds were either absorbed or thrown into deep space, and the heavy bombardment stopped. The surviving planets settled into precise paths. Saturn's ring system illustrates this transition from a chaotic debris field into an environment governed by stable, clockwork physics. The modern Earth is a distilled concentrate of elements forged by that violent history. The dense iron churning in our core and the water pooling into our oceans were collected piece by piece from those early catastrophic collisions. Every atom beneath your feet and every living creature on the surface is a survivor of that planetary gauntlet. What remains is the result of 4.5 billion years of violent persistence. Earth is the survivor of that cosmic process, a stable world born from grains of dust, the pull of gravity, and the immense patience of time.
Subscribe for more informative video like this and press the bell icon.